Today, we are celebrating the 100th episode of the Live with the Maverick podcast. And we have a very special guest to commemorate the occasion. David 𝗏𝗃𝗏 is a highly respected actuary, best known for his pioneering work in stochastic modeling, which has had a lasting impact on actuarial science, particularly in investment and financial forecasting. David's career has been defined by his contributions to the way actuaries model uncertainty, providing them with advanced tools to better forecast financial risks in an increasingly complex world. Throughout his 73-year career, David has published over 160 research papers in the field of actuarial science. His scholarly achievements have been widely recognized by honorary degrees from 𝗟𝗏𝗪 University, Waterloo University, and City University of London, gold medals from both the Institute of Actuaries and the Faculty of Actuaries, and honorary memberships of the Swiss, Italian, Swedish, and South African actuarial societies. In 2024, David received the prestigious Max Lander Award from the International Association of Consulting Actuaries for his contributions to the public awareness of the work of the actuarial profession and the promotion of the business of consulting actuaries. Welcome, David.
Hello.
It's great to have you. And
I'm here.
Great, yes, great to have you, and couldn't think of a better guest to celebrate the 100th episode of the series. So,
well, I'm not that age yet.
Almost there, almost there. So, David, I tried my best to do your career justice in the introduction, and it's no secret that you've had a distinguished career, making several contributions to the actuarial profession and wider fields. Before we discuss those contributions, let's first take a step back to understand where the journey began. So, how would you describe your early childhood and formative years?
Well, best thing is just for me to tell you a story about them. My parents were both Scottish doctors, graduates of Glasgow University. All my ancestors were Scottish. One grandfather was a headmaster of a school. Another one was an engineer. The engineer I never knew. The headmaster had considerable influence on me. But my parents, my father had got a GP practice in Lancashire. I was born there. He wanted to change practices after it when I was 3. So my mother and I went to stay with her parents, the schoolmaster in Glasgow. And there, I think probably he taught me to read and write and a lot of other things about Glasgow. Then I went to just local schools in Lancaster, where they got a second practice to begin with. And then, because I was quite bright at school, they wanted to send me to boarding schools, first of all to a preparatory school, that sort of a 10 to 13-year-olds, and then to what in England is called a public school, which isn't public at all. It's a private fee-paying school. This one called Rugby School, quite well known for the game it has given to the world, where I was there from ages 13 to 17. I was quite bright at maths and a good maths teacher, and I got a scholarship to college at Cambridge when I was just under 17, and so I left school at 17, spent a year as an actuarial student in Scottish Widows. Now, why was I an actuarial student? 2 reasons. One, the maths master at Rugby had a cousin or relative who was Phil Sparling, who was an actuary, so he knew about them. And on holiday in Scotland for a number of years, where we went to the same resort in 𝗏𝗪𝗪𝗏, north of Scotland, my parents had got to know another actuary, 𝗟𝗏𝗪 𝗪𝗶𝗀, who was at that time sort of secretary of our Standard Life, and later on chief executive of Standard Life and president of the faculty and a gold medalist of the faculty. So I knew about actuaries and started off in Edinburgh as a student at Scottish Widows, doing simple actuarial calculations, the sort of things nowadays that you don't need students to do at all, because it can be done on a computer more accurately. But I did learn there, you do everything in pairs. If you want to check numbers, you need to get two people to do it, or do it in two different ways and check them. So that's one bit of learning from the very early days. I then went to university, and because I was committed mentally to an actuarial career, I chopped and changed at university and did a year's mathematics, a year's economics, which was quite useful, and a year's English. So my degree is in English, and that has stayed with me as a permanent interest aside from actuarial work the rest of my life. Then 2 years national service, and because at university I had to amuse myself by joining the University Air Squadron, which was part of the RAF Volunteer Reserve, learning how to fly little airplanes called chipmunks, single-seater trainers. I went into the Air Force as a trainee pilot, learned more about flying on provosts, and then on vampires, which are an early type of jet fighter. I got my wings flying vampires. Never used them, of course, as a fighter. I wasn't learning how to use them as a fighter, just how to fly in them. At the end of that, of getting my wings, I spent a few months in London in the Air Ministry, which was now called the Department of Defence, in charge of a little team that was putting officers' records onto punch cards. Now, during this period, I had also spent a long vacation in Denmark in a fortnight each in 4 different insurance companies, which was organized for me by Paul Jacobsen, the then president and a very distinguished Danish actuary. And he took me to see Stephenson, J.F. Stephenson, who was very elderly at that time. He was the first actuary to be appointed at a university and was professor of actuarial science at Copenhagen University in about 1905. And I felt this was a great honor to meet someone from that far distant past, this being about 1954 or so. After national service in the Air Force, I spent a few months again doing a little actuarial job overseas, this time in the Allianz insurance, the life insurance part of the Allianz in Stuttgart, which improved my German a bit. I ended up, I'm told, with a Swabian accent. Sounds as if I come from Stuttgart, not from somewhere else. But anyway, after that, I came back to Scottish Widows, carried on with my actuarial examinations, working in the same sort of department with calculating surrender values and premium rates and stuff like that. Qualified in 1959 in the faculty. And I had also known about the Institute, and I think I'd had an Institute yearbook lying around. And I noticed that as a fellow of the faculty, I could get a membership of the Institute only by doing the final year's exams. And at that time, there was an advanced statistics exam at the Institute. So I thought that was worth learning a bit more about. I'd done no statistics at university, but I had actually done some at school in the last term after doing all examinations and things. The maths master had taught us about probability and normal distributions and regressions and stuff like that. So I did the advanced statistics paper of the Institute, which you use what was a very advanced textbook. I think it was called Ewell and Kendall, now called Kendall and Stewart, which is a seriously heavy textbook. Passed that exam, passed all the other ones I needed to, so I became a fellow of the Institute in 1960. In the meantime, I had been asked in the Scottish Widows, where I still was, to look at punch paper tape typewriters called flexowriters. And then after that, I was put onto programming in the Ferrari Pegasus computer that got, which was a seriously big machine. I mean, it's a huge thing with about five wardrobes of space, and had the equivalent of about 256 bytes of random access memory and 32K bytes of disk drive. So tiny by modern standards, but it would do any calculations that were required, and it was what people call a Turing machine, after Alan Turing, which will do anything which is, it will do anything which it is possible to do with a computer, and logically possible to do, even if it takes enormous amounts of time and enormous amounts of disk drives or punch paper tape or punch cards or some external medium. Just to finish my career before I come back to my computers, I went to Switzerland, Swiss Re, for a couple of years, nothing to do with computers there, but interestingly saw yet another continental insurance company and a different approach to things. One different approach very much of the Swiss Re was they were wanting to provide reassurance all around the world. They went to another country. They said they found out what that country wanted and they provided it. The British insurance companies trying to do business abroad tended to say, we have an excellent British product. Would you like to buy it? Not finding out what product would suit that country. You see the different approach of Switzerland and Britain. Anyway, my wife and I decided it was better to come back to Edinburgh, so I got a job at Standard Life. They very new people too, also in the programming department, and I was carried on there for a bit, then moved into as economics research manager of Standard Life, and then to just research actuary, and then realized it would be better to join a firm of consulting actuaries. So I joined R. Watson's in the south of England in about 1985. Worked there for a while, mostly doing research by now. But they decided I had reached my retirement age at the age of 62, which I thought was at least 3 years too young, if not 23 years. But I then got a part-time job consulting as a consultant at 𝗘𝗽𝗶𝗲 University, and jointly with a young actuary, Patrick Lee, helped with a new firm that he had been setting up called InQA, Investment Quantitative Analysis. And that was InQA was quite successful for a while, but has declined a bit by losing contracts and doesn't do very much at the moment. And I carried on at 𝗘𝗽𝗶𝗲, going up about for 4 days every month, not lecturing regularly, but supervising PhD students. Actually, when I was at Standard Life for about the last two years there, I had been doing some regular lecturing, which was organized by the professor of the department with Standard Life to second me as for 1 day a week to work at 𝗘𝗽𝗶𝗲. So that's roughly my employed career. I'm now unemployed, but still doing some research. You would call it retired, but I'm not quite sure whether I'm retired or not. I'm still doing things. Even giving this interview is something that takes a bit of thought. So that's my life history, very briefly.
Greatly appreciate the overview, and a few things is one, and I think I mentioned this to you before. I actually had the pleasure of visiting Scotland for the first time this summer, and it was a wonderful experience being in Edinburgh for a few days and going to the Highlands. So
Good.
recommend.
Good. It is different from England. This is one. It's very similar, and I used to think in the past that really Britain split into three. There was a section south of the Trent, which was very solidly England. There was a section in the north of England and south of Scotland that was actually rather similar, but had small differences. And there was the Highlands, which were, I mean, the east coast of Scotland counts along with the south, but the northwest coast is a different country, and historically has been almost a different country, because that was where the Irish Scots came. They were still speaking Irish, or the modern version of it, Scots Gaelic, still do in the northwest, and it's almost a different country from southern Scotland. So you need to visit both parts. My sister-in-law now lives in the Isle of Lewis, which is about as far northwest in Scotland as you can get.
I'm looking forward to heading back. One thing I noticed in your response, which I've heard several times, and it was the case for me, is how you got into the profession. It sounds like, whether it was, I think you said it was your parents who knew someone who was familiar with the profession. So it seems like many times, we have a relative or a friend who knows about actuarial science. Would you say, beyond that, would you say there were any other reasons, any other motivating factors for you wanting to become an actuary?
Well, the maths master said if you're good at maths, you can earn more money as an actuary. That seemed a perfectly obvious way of doing going into it. Whether that is true or not, I do not know. But actuaries, many actuaries earn more than many academics. So I was never tempted into a university career. I'm not researching, as I now find that researching is my forte more than teaching. I have, the research I've done has been because, as I'll explain, because it was useful I thought useful to the profession, or to the committees I was working with, and perhaps I can continue talking about my experience in that. Was that what you'd like next?
Yeah, sure. So I'm glad that you mentioned the research. So that the theme of today's discussion is actually actuaries in the research, part 2. So we're going to talk about research a bit. Now, as you know, as I mentioned in the intro, you've published over 160 academic papers, and I know you've perhaps collaborated on others. Now, when you think of your career trajectory, your long-term career trajectory, and take a step back, what were the keys to building? And I know previously we might have spoken about this, and you said it was not necessarily your intention to be a researcher, but knowing what you know now about research and what it takes to be successful and to publish papers, and what were the keys to building a strong foundation, which ultimately enabled you to be successful in publishing value-added research?
Well, I had mentioned that I was, to some extent, familiar with computer equipment, and had started learning computer programming, or code in machine code, on Ferrari Pegasus computer, and was doing that at Standard Life. But then I think Fortran, I'm not quite sure when Fortran was developed, and I started programming in 1960, and Fortran may have been around by then, but I realized that Fortran was a handier way of doing it than writing in machine code, which was clumsy. Well, it wasn't clumsy, it was just laborious. And it wasn't very clear what the code meant. You had to have a lot of explanation beside it. So I fairly quickly, although I was moving across into a different department, and that was later on, get this right, I was still in the computer department at Standard Life, but I wanted to use Fortran, and got permission to have a Fortran compiler linked onto the mainframe for my own use. Well, I got involved with the CMI Mortality Committee, Continuous Mortality Investigation Bureau, as it's called now. Then, the first thing I remember was getting involved with mortality was, I think, a paper presented to the Faculty of Actuaries about 1960 by, I could look it up, by Roland Young and Frank Reddington on the mortality experience of impaired lives, people being rated up. This was the experience of one large company, and everybody in Britain will know which company I mean, but I shan't mention it. It changed its name in effect nowadays. But a particular test that they were using was using the criterion actual minus expected, A minus E, divided by the square root of A. And I, knowing my statistics, got up at the meeting and said, excuse me, shouldn't that be A minus E over the square root of E? And for a newly qualified, or possibly even an actuarial student still, to say that Frank Reddington had got it wrong was a bit impertinent. Actually, my comments don't appear in the subsequent transcription of the meeting. But he said, yeah, he said to me afterwards, yes, I think you're right. It should be A minus E over square root of E, as everybody knows nowadays. But I then found myself appointed to the CMI committee in 1964. And the committee at that time had only 8 members, the 2 presidents of the faculty in the institute, and 3 from each side. And I and Leslie Anderson and Ernest Bromfield. No, Leslie Anderson was the president. Frank Reddington was the chairman of the committee. So I did get to work with him on a couple of meetings, really, not much more than that. And I was just chugging along on the committee, commenting on the routine papers that were being produced. And then the question came up, should we not produce new graduated tables? And what had happened in Britain was that about every 20 years or so, the committee produced a new graduated tables in 24, 29, the first ones. And the CMI committee was celebrating its 100th centenary this year because 1924 was the first year of data. They didn't know when the committee actually started, but the first year of data was 1924. Then 49, 52, and then the next ones should be about 79 to 82. And Rodney Barnett, who was the secretary at the time, had suggested one way of fitting a table was by minimizing the chi-squared value, the sum of A minus E squared over E's. I thought, well, we can do, he was doing this by repeated approximation, which is desperately slow and tedious. To do it clerically. I immediately thought, no, we can do this on the computer. And I was probably almost the only person on the committee that knew anything about computers at all. All the other people would have life officers that were starting to use them. But I knew how to deal with this. I also knew about maximum likelihood methods, which is very similar to least squares. Well, minimum chi-squared is equivalent to almost equivalent to least squares, and that's almost equivalent to maximum likelihood estimation, but maximum likelihood is a better way of doing it. So I set about writing Fortran programs to produce these graduated tables, which eventually got checked and published as what would they be? 6972 tables, and we put in some forecasting for some of them, doing the forecasting by assuming a 1-year improvement in mortality equivalent to 1 year of age for every 20 calendar years. That was how A90 and PA90 tables were produced. So that was doing very simple programming. In the course of that, I developed different formulae for doing it, which I called Gompertz-Makeham ones, GM formulae, which is equivalent really to an exponential plus, sorry, a polynomial plus the exponential of a polynomial. The typical linear model that might be used would just be 𝜇x is the e to the power of a polynomial, but putting in the Makeham part, the polynomial plus the exponential of the polynomial was a better model. It would now be called an additive model or a general additive model. So I spent some time doing that and repeated it over different years. And there was a paper which is widely quoted actually by 𝗙𝗶𝗪 𝗪𝗏 𝗪𝗏 published in 1974 on mortality graduation, which really introduced maximum likelihood estimation. People were doing it sometimes just by doing graphical graduation. You put a lot of dots in, you drew a curve and read off the values, the annual values. So what we were introducing was using 𝜇x and probably using a Poisson distribution for the residuals rather than for the actual numbers of deaths, rather than a normal approximation, which is the normal approximation is fine when there's larger numbers, but when there are smaller numbers, as there always are in a mortality table, as you get to the extremely young and extremely old ages, for an insurance company's data, not in the population, of course, but always with very old ages. The Poisson approximation is better, or Poisson assumption. So that was quite influential, I think, in constructing mortality tables. Now, that bit of research was therefore done in order to satisfy the requirements of the CMI committee. Another committee I got appointed to, because I shifted across by now in Standard Life to economics research manager. And that comes up, that's relevant when we'll come some point later. The actuaries had been involved in investment indices for a long time, starting in the 1930s. And the convention was that although they were joint, the London people, faculty and institute, looked after the share indices. The Scottish people looked after the bond indices. And the bond indices had been rather simple, too simple. And we wanted to produce some better ones. So I was on the Joint Investment Committee. And again, I knew how to write programs to demonstrate the indices and how to fit a yield curve using actually pretty well the same methods as for the mortality graduation, just curve fitting exercise, but using perhaps a different criterion, I think just least squares rather than the maximum likelihood, because it wasn't the yields were random variables. They were just irregular. They should be smooth, but were a bit higgledy-piggledy because of the bonds. I helped to construct the indices, which are still published in the Financial Times every day. The FT, now called it 𝗙𝗃𝗃 Actuaries, government securities indices. And I wrote the Fortran programs and actually supplied them to the Financial Times to use them. Well, that was, again, using my programming abilities to help the profession to produce something, these new indices. And they have chugged along happily. After a few years, I was not involved with it, then came back into it at a later stage. And Andrew Cairns and I produced a better yield curve structure, because I remember when we produced the first yield curve. It was just of redemption yields. And I said, I remember looking back at the discussion, I said we had thought of doing it in terms of zero coupon rates, but didn't want to be too far ahead of the market because they didn't know what zero coupon rates were yet. But later on, 𝗏𝗏 and I produced a model for zero coupon rates, and higher yields, which have been used by the Financial Times the last 20 years or so. And at that time, I thought it would be useful to have a good historic record. The problem with the FT is that they, as indeed lots of people in the share market, are not interested in yesterday's prices. That's all past history. What they want to know is what the prices would be tomorrow or next week, not what they were a month ago. And so they have not in the past been good at keeping historical records. And much better now because it's much easier with the computer. And there's much more interest in historical records of share prices than perhaps there was at some points in the past. So I could put together, we wanted to put together a database of the prices and yields and the index values on the government securities indices, and Andrew Cairns got some money from the Institute to pay for students at 𝗟𝗃𝗏 to go and look back at photocopied versions of the Financial Times, which weren't always terribly easy to read. And we constructed a database which has been published on the 𝗟𝗃𝗏 website until the beginning of this year, and has recently been taken over by the Bank of England to put on the, what to call it, Economic Statistics Centre of Excellence. So that's quite useful. There isn't a comparable historic record available for the share indices, which is a pity, but we could do something about it for the last 20 years or so, but they started in 1962 and the early years are quite difficult. So that also was research to help the profession, though there was nothing written. This was simply a matter of gathering data, which is a necessary part of some bits of research. Then in the CMI committee, they had set up an income protection, or what was first called permanent health insurance, now called income protection insurance subcommittee. Income protection provides cash benefits when people are sick. It's nothing to do with medical expenses insurance, but it is a sickness benefit. And the chairman of that subcommittee, a good friend of mine at the time, Jim Cairns, the father of Andrew Cairns, who's now professor at 𝗟𝗃𝗏, he died suddenly, and the committee didn't know who to appoint as chairman, so left the committee to appoint itself as chairman, to choose its own chairman, Robert Plum. But when I became chairman of the CMI, a little after that, I decided that it didn't do to have a committee with where we didn't know what was going on from the main committee. So I appointed the chairman, said the chairman is a member of all the subcommittees as well. And I went on to that IP committee, and with the help of Howard Waters, 𝗟𝗃𝗏 University, we worked out a different way of analyzing sickness. Previously, they've been using what called the Manchester Unity experience, which was constructed by the Manchester Unity Friendly Society in the 19th century, I think, and simply looked at days sick per person, per so many insured. It didn't look at the sickness rates and recovery rates. It wasn't thinking in terms of a multiple state model going from healthy to sick then either to recovery or dead, and from healthy you might go to dead as well. And so Howard Waters knew all about Markov, these Markov or semi-Markov models. And it took a long time between us to graduate the recovery rates and mortality rates from the sick, and to find the sickness rates, and to calculate the model and to explain it to other people. And one of the problems the three of us were helping was Phil Bayliss, who was doing some of the graduation, and Howard Waters checking it, and I was doing graduations. We disagreed on what a week was. Howard said there were 52 weeks in a year. Phil Bayliss said there were 52.18 weeks in a year, which is correct on average, allowing from leap years. I said there's 7 days in a week, so it's 1/7/365 of a year. And because we were using slightly different definitions, we couldn't get agreement with our answers. Because when we looked at the rates at weekly intervals, they weren't the same. So it is quite interesting how one has to be terribly careful about definitions and how things are calculated. Anyway, that eventually, all of our work on that eventually got published in CMI Reports number 12, and the IP committee has continued with it, the new methods since then. In fact, in order to help it, I produced quite a lot of the programs. This was the time I was in InQA. I produced quite a lot of programs used by the IP committee. I think they've modernized it all and moved on to something else, but I was producing Fortran programs for them on a commercial basis there. But sometime in the early 80s, AIDS turned up. And it so happened that because my wife was doing some research, she's a sociologist, not a medical doctor. She was doing research for a PhD with genetically inherited diseases in Glasgow Royal Infirmary. And although her main interest was APKD, acute polycystic kidney disease, a nasty disease inherited from one generation to the next, she was also interested in hemophiliacs, which is another hereditary hereditary disease. And the chief doctor in the hemophiliac department came in one day and said, I've been in America, I think there's a problem. I've been learning about this new disease called AIDS, or HIV infection, and we need to see whether we've got it in with the hemophiliacs here, because the hemophiliacs can have their symptoms greatly alleviated by injections of what's called factor VIII, which is a condensed factor found in the blood of other people, but you need a lot of blood donors, and quite a lot of blood donors were infected with HIV, and so many hemophiliacs received this infected blood. And my wife's Patricia's job in this was to talk to them and explain about safe sex, for example. She had to, it was ending up taking in bottles of condoms to supply people with, and talk about it with them as doing a sort of social work job there. But because of that, I knew about it, and it was realized it was quite easy to program it using the IP sickness model, but putting in the relevant bit for infection, because with sickness, you assume that sickness just depends on somebody's age, and they will get sick or not sick depending on their age. It obviously depends on a lot of other things, but all that we knew about was age and sex, perhaps numbers of years insured. But with infectious diseases, it also depends on the number of people infected. So you have a cross product. You've got to bring in the number of people not infected who could get the disease, the number of people infected, and multiply those two numbers together and with another coefficient. It's actually very similar to a marriage model. If you imagine two groups of people who are eligible for marriage, who like not married males, not married females of different ages meeting, and there's a small, every time they meet, there's a chance of them deciding to get married. So the mathematics behind a marriage model is the same as mathematics behind an infection model. I'm not suggesting that marriage is an infection, but that's a different matter. Anyway, that took up some time as well, because I got involved with the AIDS working party of the Institute. And I could follow found it not too difficult to program, making for the assumptions that the committee wanted. Now, I think we got our estimates of number of people who might die from AIDS grossly too high. I felt that was better than getting grossly too low. If you get them too high and scare people and they go in for safe sex, then that's good. If you say don't worry about it and they don't go in for safe sex and the numbers are then a lot higher than you thought they were going to be, you've done it the wrong way around. So I didn't mind that the numbers were less than they might have been. We'd alerted people to helped to alert people to dangers. It was actually only just 4 years ago when COVID turned up, since I knew about infection models, it was just very quickly I could write down and put into Excel a very simple COVID infection model that lasted with one line of Excel per day. And that's how I think Annie 𝗘 found out about that and got me involved in giving a webinar on it to the AFIR ERM section, or through for the IAA, and then got me involved in a working part of the IAA on of the AFIR section of the IAA on lessons learned from the epidemic, which I can come on to next. And so all these things of mortality, IP, AIDS, and COVID have all just followed one from another, because each one is an extension of the same sort of thing. And for COVID, for the working party, 𝗘𝗽𝗶𝗪 Shaheen and I have been doing something different. What we decided to do was look at the history of mortality rates in countries which had not been affected by the world wars, but had good data. And we found 3: Sweden, Spain, and Switzerland. Spain had a civil war, so it had a lot of deaths in the late 1930s, but they were all in Spain. The trouble with this First and Second World Wars is that so many of the deaths were in other countries. Huge numbers of people from Britain died in France and Belgium, in Flanders, France and Belgium. Huge numbers of Germans died on the Western Front, on the Eastern Front, as well as on the Western. And so many countries changed their boundaries as a result of the war, so that made it difficult to use. And additionally, the Spanish flu epidemic of 1918 had not been really recorded in the countries which were fighting, because it was probably widespread in the trenches, but the deaths in the trenches on both sides were just put down to French fever or something. You didn't notice that it was this new infection. It was in Spain in particular that it was noticed and identified as a new infection. It didn't start in Spain. It was just first publicized in Spain, and sadly the king there caught it and died. But what we did here was take the population data from the human mortality database, fit a Lee-Carter model, which population people know about. That gives 2 parameters for each age and 1 parameter for time. And it's too simple what we did, because it doesn't pay attention to the age distribution of the infections, which I can come back to. But what we did was pick up went back to 1908 for a year before the Spanish flu, and finish in 1919, the year before COVID. And we used the 𝗘𝗶𝗃, the time series, the time coefficient, analyzed out using time series models, which, as I'll explain later, is very much the same sort of arithmetic as for the investment models, where I've got annual series of rates of inflation or something. This is just annual series for mortality. And in order to allow for the big jump up in 1918 and back down again in 1919, as appeared in these 3 countries, we had to use fatter tail distributions. It clearly, the common assumption, and the assumption I'd been using in the Wilkie model, which we'll come to later, was for normally distributed residuals. Well, these clearly were not normally distributed, so we had to find fatter tail distributions. And Laplace distribution was quite a good one, but even that proved to be not quite enough. We found that on our assumptions for Switzerland and Sweden, if an insurance company had used the data up to 1919 to forecast 1920, the actual COVID experience would have come within a 1 in 200 probability. But for Spain, it was much bigger. In fact, both the Spanish flu in Spain and the COVID in Spain were much heavier, about twice as heavy as in Sweden, and with Switzerland somewhere in between. So what we're doing on that front is trying to find suitable fatter tail distributions with higher kurtosis. Kurtosis is the 4th moment divided by the 4th power of the standard deviation. So it's a measure of the fat-tailedness. And for a normal distribution, it's always 3. For a Laplace distribution, it's always 6. For a skew Laplace, it can get a bit higher than 6, but not very much higher. But we were getting kurtosis of 15 or so. So that wasn't satisfactory for the COVID modeling, and an alternative we've been looking at there is a mixture model. Assume X1 and X2 are 2 random variables, both, for example, normally distributed, but there might be any distribution, Laplace, skewed Laplace, or something else, hyperbolic. And Y is a random variable which is equal to X1 with a probability P and equal to X2 with a probability 1 minus P, or Q. And that can get much fatter tailed, and we're still working on that as a way of modeling the past mortality. And as I'll mention later, this helps also modeling past investment experience, which can also be much fatter tailed than normal. And so I've been talking about that without bringing the Wilkie model in, because the Wilkie model is so different, and also requires a rather longer story to explain how I thought of it and how the different bits of it come in, and a lot of other things. But that I think has explained my motivation in, at least first, my accidental getting involved with computer programming, or now called coding, perhaps, but both the program design and the coding, and how I took to it and used it for practical purposes in mortality, investment indices, income projection, aids, all for the benefit of the profession, and COVID more recently for my own interest, and also for the interest of the profession too, and what we're doing on the long-term modelling of mortality. I'll go back for a moment, just mention forecasting. I mentioned that we did do some forecasting with the annuity tables in the 1980s, 1970s. And later on, John McCutcheon and I did a different method. But the CMI has now got a much more elaborate forecasting method, also deterministic, I think it's, and there's the deterministic way of looking at a mortality table is that you start with 100,000 people and so many die, that's D0, and in the first year, so many die in the second year, that's D1. But we know that these are really only probabilities, and numbers that die are random variables. And if we're wanting to do some forecasting, we would want to bring in the Poisson number of deaths, or normally distributed number of deaths, which may be important for some small pockets. I remember when I was at Watson's, the actuary who was dealing with the British Rail Pension Fund said it so happens that British Rail is structured that all the previous railway companies have kept their own pension funds. They haven't been amalgamated. So there's a pension fund for the old Great Western Railway pre-1923, I think, and the old Great Northern, and they have got about 10 people in them. And should we not allow for some uncertainty in how long they might live? And I said, well, yes, the safe thing is just to value them as if they're all annuities certain to the age of 105 or something like that. But one could use stochastic methods for valuing very small pension funds, or if it was necessary to keep them separate and not amalgamate them with something else. So that although so much of it has been deterministic in the mortality rates and what I've been doing, you can bring stochastic modeling into it too.
That's a really good overview of, you know, some of the modeling that you've done. You talked about mortality forecasting, the investment indices, income protection, and the key theme there is that these were enabled by your early adoption and promotion of the power of programming. Now, I'm curious to get your thoughts on the evolution of programming. We talked about, you know, programming, coding, and how that's done in insurance and risk management today. A couple of things I'll mention. Of course, open source learning is very common, and what's interesting, and you'll hear the CEO of NVIDIA, he said this a couple of times, is with this low code, no code paradigm that not just this industry, but a lot of industries who use computing, who rely heavily on computing power, are moving to where you can actually execute code without writing a single line of code. I'm just curious to get your thoughts on that, because that's very different, I think, today than it was perhaps when you started.
Well, yes, but and come on to that later too. But even with AI, they talk about programs learning or programs writing routines. Well, these are not. It's not somebody has written the coding of a program which will alter some numbers or some bit of code elsewhere, so the machine apparently learns, or the master program that somebody has, some computer programmer or coder has written, will take in instructions and knows how to construct a coding or subroutine to do that. But that's because the coder in the first place has set up a complicated program which can write other programs. This happens. This can happen with a compiler. You write some code in Fortran. You put it through a Fortran compiler, which constructs a machine code version of it. Everything is in the computer is actually carried out in machine code. You can have an interpreter program where you give it line by line, and it doesn't construct a machine language program, but it takes the code in line by line and constructs the machine code to obey it. It's usually much slower than having a pre-compiled version, but all of it, whatever the top level program is doing, at the bottom level is just machine code moving around noughts and ones, nothing else.
Yes. No, lastly, one thing I wanted to ask about, you've been in the profession, or you spent a lot of years in the profession. As you reflect on your actuarial career, what do you think was the most significant development in the profession?
Oh, computers. When I started work in the Scottish Widows in 1951, the actuarial department had about 20 actuarial students in it, split into 10 pairs, called a boat. And we went round, we got in a bundle of requests. Please calculate surrender values or loan values for these policies, letters usually from banks or solicitors. We went round gathering the data from the policy registers or other registers to see what premiums had been last paid, calculated the surrender value, either sometimes using log tables or calculators or very long cylindrical slide rules, and checked that we got the right answers, and the pair of us could do perhaps 30 a day. That could be done in seconds. Now with one person putting in the policy number and accessing the database, and those jobs have disappeared. Different jobs have been created in the programming coding departments. So it was also possible with the computer to do valuations every year. Previously, even with punch cards, it was so laborious that you might do a proper valuation every 3 years or so. You couldn't declare bonus every year because that involved the entire staff doing overtime for 3 months to do individual calculations. And so I think programming has made a huge difference to the way that actuaries think, and because of what I've shown as ways of opening up different ways of doing things, that has made a great change. Previously, you could only do things which you could do with either an army of clerks or clever algebra. Now you can do it with a computer. And you don't need the army of clerks. You don't need to be too clever with the mathematics. You can do it approximately.
Yeah,
that's what I see as the change. But that's perhaps what I see and what I've done. If other people may see other quite different things.
Yeah, it's hard to argue with that, I think. Very timely observation. So just to recap what we've spoken about so far, we've learned about David's background growing up in Scotland, how he got into actuarial science, how he was an early adopter in utilizing the power of programming to utilize models to make a difference, not just for insurance companies, but in the broader society as well. And David talked about the importance of programming and computers, more broadly speaking, in terms of being one of the biggest changes within the industry or within the profession throughout the course of his career. So this concludes the first part of our interview. In the second part of our interview, we're going to be going into the famous Wilkie model and exploring the realm of modeling uncertainty. So going into the realm of stochastic modeling. So Thanks for joining us, and you can continue to watch in part 2. Thank you, David.
Thank you.